I'm super excited to introduce our first main stage speaker today. And our next session is suitable for both technical and non-technical audiences who are curious about data-driven decision making. In the next 20 minutes, you will learn several statistical rules of thumb that you can use in everyday work. For example, how many ratings do you need to trust a seller on Amazon? You will also discover how to do statistics when you not only have a small sample size, how to interpret ratings with confidence and estimate the chance of something that hasn't happened yet. I'm adding Annie Gu from Yelp. Hi, Annie.
Hi, everyone. I'm Annie. I'm an applied scientist at Yelp.
Yes, and I'm going to add something about your impressive bio. So, as Annie mentioned, she's a plus scientist at Yelp who believes in the power of statistics. That's why she's talking about it today. At work, she uses statistical experiments and machine learning to decide the best pricing for ad auctions and detect identity fraud and suspicion transactions in financial markets. In her spare time, Annie teaches programming to women who want to make a career change and participate in data hackathons to help charities make data-driven decisions. So welcome, Annie. Welcome, Annie, on this stage. And I'm going to add your slide just in a moment. And everyone, please enjoy practical statistics for running experiments. Annie, I'm going to be back at the end of your session. The stage is all yours.
Sounds good. Thank you, Anna. Hi, everyone. My name is Annie. I am an applied scientist at Yelp. And today we're running through a short 20-minute workshop to show you some easy statistical rules that you can use both in your work as well as your day-to-day life. So a quick look at the agenda is that we will go through 4 rules. The first is called the power of small samples. It's called the rule of 5. The second one enables you to read ratings from things like Amazon and Netflix. The third rule allows you to do a quick estimate of when anything will double in terms of growth. And the last rule we'll learn is how to estimate the probability of something that has not happened yet. So the first rule, the power of small samples. So imagine that you are now working for a tech company with 10,000 employees, and you are tasked to find out how much time the employees spend on average filing expense reports per day. And so how would you do that? Obviously, the first thing you can do is you can run a census. So you can send an email to all 10,000 people to say, hey, everyone, how much time do you spend filing reports per day? But the problem with that is obviously quite clear. First, you're going to pass an email to everyone. So you probably need to get a lot of management approval for that. And more importantly, you are going to get a pretty biased sample because the people who are most likely to respond to your census are probably the people who spend a lot of time filing reports. And the people who do not spend much time filing reports, they're probably just going to ignore your email. This means that the result you're going to get is going to have a survivor bias. So the result you have will probably be an overestimate of how much time people actually spend filing report. So census might not be a very good solution. So instead of sending an email to everyone in the company, one quick rule you can do is to pick 5 random employees and ask them what their median report filing time is every day. And let's imagine that the results that we get are those 5 that's described on the screen. Can you use this sample of only 5 to estimate the median of every employee's filing time? So you can see that 5 is obviously a very, very small sample of the 10,000. So you might think that it's probably unlikely that the 5 can represent all the 10,000 employees that we have in the company. However, the first rule that I will introduce today is called Rule of 5, and it says that there's a 93% chance that the median of a population is between the smallest and the largest value in any random sample of 5 from that population. In the case of the employee filing expense report, it's saying that if you take 5 random people and ask them what their sample expense filing time is, there's a 93% chance that the whole company's median expense filing time is going to be between the smallest and the biggest from the 5 random samples. So here is a quick proof of the rule of 5. It is saying that if you randomly pick a number, in this case we have 10 to 26. If you randomly pick a number that's above the median, the percentage of that probability is going to be 50%. And therefore, if you pick 5 numbers that's all above the median, then the probability is 50% to the power of 5, so that's 3%. And similarly, if you pick 5 random numbers and all 5 is smaller than the median, then it's going to be another 3%. So therefore, the probability of the median value to be between the smallest and the highest of the random 5 samples is going to be 1 minus 3% times 2, which is the 93% that we have here. So here's the mathematical proof of the rule of 5, but I have tested it a few times in my job. So first thing I did is I picked 5 colleagues and I asked them, how much time do you spend to commute one way each way? And then they give me the 5 numbers that you see here. This is obviously based in the UK because I am based in London. And you can see that in this random list of 5, 15 minutes, 60 minutes, and etc., the smallest is 15 minutes and the biggest is 60 minutes. And it's saying that there's a 93% chance that the median UK commuting time is going to be between 15 and 60 minutes. And that is actually correct because I went to the National Statistics Bureau's website, and it turns out that the median commuting time for us here in London is around 27 minutes one way. I've also done other things to ask people like, how much time do you spend cooking, how much, and etc. And this rule tends to be quite useful. So what this means is that you can use this rule of 5 to apply to samples from any distribution, and it can also be extended if you have more than 5 random samples. So if you have 6 samples or 7 samples, you can also apply the rules to get an even tighter bound for the estimate. So what this first rule tells you is that you do need data to get certainty of the hypothesis, but you need far less data than you think. So what this chart is showing on the x-axis is the number of samples, and the y-axis is the error bar. That is how much error there is in your estimate. And you can see that the line decreases pretty dramatically from 5 samples to 25 samples. So it's still telling you that if you want to test a hypothesis, you will need data, but you might need far less than you think you will need to actually test it. So this is the first rule. The second rule we're going to go through today is about how to interpret ratings. And I think that most of us will encounter that on a regular basis. The example that I have here is about buying a handbag, because we are at a woman conference, so I thought that most of us might be interested. So here we have 3 very fancy Chanel handbags. So the first one is from a seller which has 100% positive rating and 10 reviews. The second one is from a seller with 96% positive rating and 50 reviews. The third one is a seller with 93% positive rating but 200 reviews. So as you can see, there are the more reviews a seller has, the lower the rating it is in this example we have here. So natural question we have is, which one should you buy from? Because naturally we feel like the more data we see, the more confidence we have in given rating. So in the case of the first seller, they have 100% good reviews, but they only have 10 reviews. So you might get a little bit fishy and think, oh, maybe they have fake reviews, maybe they just got lucky. How do I make the trade-off between having more data, which gives me more confidence, versus having a lower rating, which means that the service might not be very good? So there is a quick way to do that in mathematics. So the way you can do that is, if you see an advertiser with 10 positive reviews, 10 out of 10, what you can do is you add 1 more positive review and 1 more negative review. So instead of saying 10 out of 10, you actually calculate it as 11, which is 11 positive reviews out of 12 total reviews. So this gives you the number of 91%, which is a true estimation of what the good review rate is. So this is the rule. So it's the positive plus 1 divided by the total rating plus 2. Okay, so you might think that this looks very simple. What is the mathematical proof for it? So actually, before I show you the mathematical proof, you would apply this to all the 3 sellers. And in this case, you would the second seller is probably your best bet, because after doing the correction, it has the highest good rating at 94%. So next, here is the mathematical proof. So this is called Laplace's rule of succession. It was invented by this dashing young lad on the right-hand side called Pierre Simon Laplace. He is a French mathematician that invented a lot of things, one of which is this rule of succession. And it's saying that, I'm not going to read the rules, essentially it's quite long, but it's saying that every time there's a probable opportunity for an event to happen, in this case, a positive rating, then it occurs with the true probability of P, which can be estimated by K plus 1, K in this case being the probability of a positive event, and N plus 2, which is the probability, for which N is the total number of events. The deduction of this rule is slightly complicated, so I have included a proof on the right-hand side here for those of you who are mathematically curious and want to prove it yourself. There are 4 rules involving stats that's used to prove it: law of total probability, Bayesian theorem, binomial, and as well as beta distribution. So if you don't want to remember it, that's kind of what I do as well. I just apply the rule. So when I see an Amazon rating, I just do K plus 1 and then N plus 2, and then I try to derive like a total rating myself before I do the purchase. So here we have another example. Let's say that you want to buy a book and you see 3 sellers. The first seller has 100% positive reviews with 14 reviews. The second one has 96 positive reviews with 500 reviews. And the third one has 95% with 2,000 reviews. Which one should you buy it from? So in this case, you would apply Laplace's rule. So for the first seller, you add 1 to 14 positive reviews. So that's 15 on the numerator. And then you add 2 to the denominator, which gives you 16. And so that's how you get the 93% for the seller 1. And then you do the same thing for all the other 2 sellers. And in this case, seller 2 is again your best bet, because after correcting for the bias, they still have the highest rating overall. So that's the second rule. The third rule we are going to go through is called how to estimate growth by rule of 72. So imagine that you are launching a new product and you are the dedicated product manager. So the product has been beta mode for 3 months. And currently it has about 100 users. Based on historical data, it has achieved an average user growth rate of 12% per month. So as you can indicate it here, month 0, we have 100, month 1, we have 112, etc., etc. Then someone asks you quickly, what do you think, how long it will take for the number of users to double? So the quick rule you can do on the back of your envelope here is called rule of 72. It's very widely used in finance, and it's used to estimate the doubling time of an object. So here, if you save £10 in a savings account and the interest rate is 2%, then it will take 36 years, which is 72, divided by the growth rate to get the £10 to £20. So the formula is on the lower left-hand side here. The time it takes for something to double is roughly 72 divided by whatever the growth rate it is. So going back to our problem earlier of estimating user growth, to answer the question, you will know that the user growth rate per month is about 12 months. So you will tell the director of product that it's going to roughly take 6 months, which is 72 divided by 12, for the user to double every time. So every 6 months, based on the current growth rate, your user base is going to double. The rule of 72 is applied on exponential growth, and it can be used in a lot of ways. So I have used it, for example, to quickly calculate, like, when will the company's revenue double, how long do you need to save versus invest to get enough deposit for your dream home, etc., etc. There are several variants of the rule. There's rule of 72, 70, and etc. They all refer to the numerator of the formula. Most people use 72 because it has the most it's the most easily divisible. But if you want, you can also do this 69.3, which is the most accurate, but it's probably going to be difficult to divide that number by a gross number. All right. That will take us to the last rule that we'll cover today. So this is how we can estimate the probability of something that hasn't happened yet. So imagine that you are a solution engineer and you're pitching your company's product to new clients in a country called Wakanda, which you haven't been to before. So imagine you pitch to 20 clients and you find that 7 who are interested. You may estimate that the chance of getting a deal in Wakanda is 7 divided by 20, which is around 35%. But imagine that if you pitch to 20 clients and none of them is interested. Are you willing to say that the chance of getting a deal is 0 by 20, which is absolutely no deals in Wakanda? How would you quantify that probability of something that you haven't seen yet? So this rule is called rule of 3. It gives us a quick and easy way to estimate these type of probabilities. So it says that if you have tested n cases and still haven't encountered what you are looking for, then the probability of that happening is going to be less than 3 divided by n. So in this case, if you have done 20 pitches and you have got 0 interest, then the probability of clients in Wakanda being interested in your product is going to be less than 3 divided by 20, which is 15%. So the mathematical proof is kind of on the right-hand side. You can see here that the rule of 3 is represented by the purple line, while the exact binomial distribution is represented by the orange line. And you can see that the 2 lines gets very close very quickly as the sample size increases. So the assumption for rule of 3 is that the underlying data is binary. That is, you can only get a yes or no for whether the client is interested in your product, and that the probability of an event is fixed. So this is very useful when I was working in banking, because we were doing a lot of fraudulent transaction monitoring, and fraud does not happen a lot. So when you sampled 100, you might find no fraud, but you can't really say that no fraud happened at all in the sample. So we use this rule of 3 a lot to do quality assurance, frauds, and looking for anomalies. So lastly, we have a very simple example. As a software engineer and you're trying to fix a bug for a unit test, you have run it 100 times and the unit test hasn't failed. How can you assign a probability that a unit test is not fixed, even though you have run it 100 times? Applying for the rule of 3, you can say that I've tested 100 times. It works in each instance. Therefore, I can say that the probability that the unit test is not fixed is less than 3%, which is 3 divided by 100. And that brings us to the end of the talk. Thank you very much. I think we have 2 minutes. So if anyone want to have questions, I'm here. Yeah, that's it. Anna? All right, let me look at the comments. One moment.
Hi, great session. It was so easy to follow and very interesting. I think now we all, when we go to, to get a handbag, we know how to decode that very tricky reviews and don't be fooled by 100% good ratings. And I think it counts for so many ratings in restaurants or like TripAdvisor, right? So we would not really be fooled by the stats. So thanks so much. It was a really practical example of how we can, how data and how some stats actually could be very tricky to decode if you don't know. So thanks for sharing that. And we have just 1 minute, I believe. So let me see if we have any questions. I see that people were just tuning in and taking notes and so into your presentation. Thank you so much. And very, very important question, will we get the slides? Because everyone just loved the presentation.
And how do I share the slides? What's the best way?
We can share in the chat if you have like a shareable link. We can share them later.
Yeah, I will add them to the comments after the talk. I will put it on GitHub,
Yeah. Fully packed with useful tips, simply presented. Many thanks and well done. So you nailed today. We're now, very energized and very kind of empowered how to do it right. So thank you so much, Annie. It was a pleasure to have you. And make sure to drop by Yelp's booth, say hi in the chat. And I know, maybe you work with Annie tomorrow. Yeah, that would be awesome. Fantastic. So Annie, you have a great day. Make sure to connect with some of the people, go to one-on-one network, and I'm sure they would be very happily surprised that they connect with you. So you can directly connect with Annie, find Annie in the people tab if you want to say hi. Annie will probably also drop your LinkedIn profile if that's okay with you.
Yeah, I'll
Okay.
do it with the slides. Yeah, thank you.
Okay. Awesome. Thank you. Bye, Annie.